Section 6.1 is on counting, and there's the count because Sesame Street's awesome. Okay, we're going to start out with something called the multiplication rule, and the easiest way I think to see how this works is to just jump right in with an example. So suppose you are getting dressed in the morning and you have 3 shirts you can choose from. We'll say you have a red shirt and a white shirt and a green shirt. And you have 2 pairs of pants you can choose from. Say you have jeans and you have khakis. So you have a very limited wardrobe, but you're not very creative. So basically you're me getting dressed in the morning. I want to show you one way you can write out explicitly all your choices, and then we'll kind of look at a little bit more abbreviated way to do that. So you can use what's called a tree diagram, where you list off all the possible choices. So first thing you'll do is you'll pick out which shirt you want to wear. So there are 3 choices here. So you can go red, you can go white, or you can go green. And those are the first set of branches on your tree. Once you've made that choice about your shirt, then you have another choice to make about your pants. So you can choose jeans or khakis. And now we have outfits. We have an outfit where we have a red shirt and a pair of jeans. You have a red shirt and a pair of khakis. Same thing with the white. You can choose jeans or you can choose khakis. So you'll wear white shirt with jeans or a white shirt with khakis. And same thing over here. You can choose jeans or you can choose khakis. So you'll be wearing a green shirt with your jeans, or you'll be wearing that green shirt with your khakis. And so we can count out how many different outfits there are explicitly. There are 1, 2, 3, 4, 5, 6. There are 6 different outfits. But there's a little bit faster way we can do that. Notice that there are 3 choices for the shirt and 2 choices for the pair of pants. So the quick way is what the multiplication rule is. You can pick 3 pairs of pants multiplied by 2 different, you can pick 3 shirts times 2 pairs of pants and get a total of 6 different outfits. And this always works when you have different ways something can be done and you want to do both of them. That's summarized in the multiplication rule, or the product rule. The product rule says, suppose a procedure can be broken down into a sequence of 2 tasks. If there are n sub 1 ways to do the first task, and for each of these there are n 2 ways to do the second task, there are n1 times n2 ways to do the entire procedure. So in that silly made-up example I have, there were 3 ways to do the first task, which was picking out a shirt, and then once you know a shirt, there were 2 ways to pick out a pair of pants. So there were 3 times 2 ways to pick out an outfit. That's the multiplication or product rule. Let's look at a couple more examples. All right, how many license plates are there that consist of 4 letters followed by 3 digits? So what we're doing here, the tasks we're doing are choosing possible combinations of characters for a license plate. So for the 4 letters, the way I tend to do this is I kind of put parentheses down for my choices, because I'm choosing a first letter, and then a second letter, a third letter, a fourth letter. Then I'm choosing a digit, a digit, a digit, and a digit. So there are 26 ways I can choose the first letter, 26 ways to choose the second letter, 26 for the third letter, 26 for the fourth letter. And now all my letters are done. So now I'll move on to the digits. And the digits are 0 through 9, so there are 10 ways to choose the first digit, 10 to do the second, and 10 to do the third. So the number of license plates are just 26 times 26 times 26 times 26 times 10 times 10 times 10. So that is 26 to the 4th power times 10 to the 3rd power. And that is equal to, let me quickly do this in my head, 456,900,000 976,000. So, and I totally did that in my head. So that's how many license plates there are that consist of 4 letters followed by 3 digits. Okay, let's do another example that's a little more abstract. So, how many functions are there from a set with m elements to a set with n elements? So I have a set over here on the left that consists of 1, 2, 3, 4 m elements. So let me call this set A, and the cardinality of A is equal to m, and I want to define a function that goes from A to another function that I'll call B, I guess, and the cardinality of B is going to be equal to n. So it's going to have n elements. So it's going to have 1, 2, 3, n elements. So how can I count how many functions there are? Well, look and see how many choices you have for the elements. So this first element in A, this guy right here, can get sent by the function to this first element in B. I can send it to the second element in B, the third element in B, and so on and so forth. Or I can send it to this nth element in B. So the first element can get sent. I have n different places I can map the first element to. And then I'm going to multiply that by the number of choices I have for the second element in A. So the second element in A, this one right here, can get sent to the first element in B, the second element in B, the third element in B, and so on and so forth. So the second element in A, there are also n different choices for that one. So maybe you've noticed the pattern here. Let's do it one more time though. This third element can get sent to the first guy, the second guy, the third guy, down to the nth guy. So there are n different choices for that one. And that's going to be true for all of the m elements that are in A. So it's n times n times n times n. And this happens, this multiplication happens m times, because that's how many elements there are in A. The first element, n choices. The first element, there are n choices. That's where that n came from. The second one that's colored green, there are n choices. That's where that n came from. And so on and so forth. And so these get multiplied together m times. And so the answer to the question, how many different how many functions are there from a set with m elements to a set with n elements? Well, it's just n times n, m times. So this is n to the m power. Okay, now we have something called the sum rule. So let's read what it says first, and then I'll use this Venn diagram to kind of give you the intuition behind it. So the sum rule says, if a task can be done in either n1 ways or n2 ways, where none of the n1 ways is the same as the n2 ways, that is, there is no overlap. Okay, these n1 ways are going to be represented by things in the set A, and these n2 ways are represented by things in the set B. And notice that there's no overlap between those two sets. The n1 ways, none of them are the same as the n2 ways. Then the number of ways to do the task is just n1 plus n2. You literally just add them up. Okay, you literally just add them up. So the way I want you to think about it, because this will be relevant in just a second, is we count the number of ways to do the tasks in A, represented by these horizontal lines, and there are n1 ways to do the things in A. And then we count the number of ways to do the tasks in B, represented by these red vertical lines. Okay, so we count all these, and there are n2 ways to do those. And so that means that the number of ways to do both tasks is just, well, you just add them together. To do both of them, it's going to be N1 plus N2, which is, right there. So that's how many ways to do both tasks. You do all the tasks, and you count the ways to do the tasks in A, in one of them. You count the ways to do the tasks in B, in two of them. And so the way to do either the tasks in A or B is N1 plus N2. Again, where there's no overlap between the tasks. All right, let's just see one quick example of this. Okay, suppose that there's a committee that has to be chosen, and you have to choose someone from the math faculty or someone from the iTech faculty to be on the committee. How many choices are there for the committee member if there are 35 math faculty and there are 22 iTech faculty? Well, you're only choosing one person. You're only choosing one person to be on the committee. So the number of choices you have are 22 people from the iTech committee plus 35 people from the math committee gives you 57. So the dean or whoever it is makes the choice for a committee member from math or iTech to be on the committee. The dean has 57 different choices for the person to be on that committee. Okay, now let's see what happens if there is an overlap between the two different tasks. And this is called, the book calls it the subtraction rule. So again, let's read this explanation and then look at the Venn diagram for a little bit of motivation. If a task can be done in either N1 or N2 ways, then the number of ways to do the task is N1 plus N2 minus the number of ways to do the task that are common to the different ways. So let's go ahead and name these sets A1 and A2. And the formula is given right here. It's the cardinality of the union of A1 and A2. This is what we're trying to count. It's equal to the cardinality of A plus A1 plus the cardinality of A2 minus the cardinality of the intersection. So let's see why that has to be the case. So I'm going to go ahead and color A1 red this time. So I'm going to count all of the ways to do this thing that are in A1. So drawing these red horizontal lines means I'm counting all of the elements of A1. And now I'll use, green, I guess. Yeah, green. Make it Christmas, red and green. Now I'm going to count the number of ways to do the task in A2 with these green lines. So I'll draw vertical green lines to represent doing everything in A2, or another way to think of it is counting all the elements in A2. Let me draw them a little bit closer together. So what happens when we do that is we've counted everything in A1, and we've counted everything in A2, but look at this part in the middle. Look at this part in the middle. This part, this little football shape, has been counted twice. It's been counted once by counting A1, counted a second time by counted A2, when I counted A2, so it's been counted twice. So to fix that, to get the right count, I subtract off that intersection. I subtract off the cardinality of that intersection one time. And so that's the subtraction rule. Let's see an example. Okay, think about a standard deck of cards. I want to see how many kings or hearts there are in a standard deck of playing cards. So if you don't recall, a deck has 4 kings. There's the king of spades. There is the king of hearts. There is the king of clubs. And there is the king of diamonds. So if I want to count the number of ways, or if I want to count the number of kings or hearts in a deck, then I would count the number of kings plus the number of hearts, and then subtract off the number of cards that are kings and hearts at the same time? Well, this is easy. There are 4 kings. There are 13 hearts, because it's the ace of hearts through the king of hearts. And there is 1 card that is a king and a heart at the same time, and it's the king of hearts. So when you do the arithmetic, 4 plus 13 is 17, minus 1 is 16. And I really did do it in my head that time. Okay. Another example. Suppose I want to count how many students there are, and the data that I have, how many students are in a class, and the data that I have are, the student has 20 iTech majors, 10 math majors, and 5 double majors. Well, I have a set of iTech majors and a set of math majors, and there's an overlap. So to count this, it's going to be the number of iTech plus the number of math minus the number of double majors. Because when I count the iTech, I'm counting the double majors. And when I count the math, I'm counting the double majors. So the doubles have been counted twice. So I've got to subtract them off once. All right, again, this is pretty quick and easy. 20 iTech majors plus 10 math majors minus 5 double majors gives you a total of 25 total students in the class. Okay, we've had a product rule, a sum rule, a subtraction rule, and there's a division rule. So this one looks the weirdest when you try to read the explanation from the book, but it really isn't that bad, and I think you'll see that when we do this example. So the division rule says there are n divided by d ways to do a task if it can be done doing a procedure n ways, and for every way, d of them, d of the n ways correspond to the same way. So let's look at this example, okay? How many ways are there to seat 5 people around a table where only neighbors matter? Okay, so let's put a table right here where we're going to sit people around it, okay? And there are going to be, let's see, there are going to be 5 people seated around this table. So I'm going to put a circle for each of the 5 people. So 1, 2, 3, 4, 5. Okay? Now, all that I care about is how many ways I can seat these 5 people. So for the first seat at the very top, I have 5 choices. Now, once that first person is seated, they're not going to sit anywhere else. So for the second table, I have 4 choices. For the third seat, I have 3 choices. For the second seat, I have 2 choices. And for the last seat, I have 1 choice. So it looks like there are 5 times 4 times 3 times 2 times 1 different choices for how I can seat these 5 people around a table. But notice in the problem, we're told only neighbors matter. Okay, so I don't care which particular seat a person is sitting in. All I care about is who is sitting beside them. Okay, so what I'm going to do now is I'm going to write down letters to represent people's names. So I'm going to have person A sitting right here, person B, person C, person D, or person E. So that's the arrangement that I have starting out. But look, I could have, let's look at another table right here. Sorry about the green outline, that's the color I had chosen. I could arrange them in a different way. I could arrange person A sitting right here, person B, person C, person D, and person E. Okay? Now, they're all sitting in different seats, but all that matters is who their neighbors are. So in this arrangement, A has neighbors B and E. And in this arrangement, A still has neighbors B and E. Okay? So these are considered the same way to seat those 5 people around. I could rotate them around again where person A is sitting right here. person E and person B, that would be the same way again. So I can arrange A at any one of these 5 places, and as long as the same people are sitting beside of them, it's the same way that they're sitting. It's the same way. So if we apply the division rule to this, how can we apply the division rule to this? We go back to our first way of counting over here. Okay, so we counted that there are 5 times 4 times 3 times 2 times 1 choices to sit them down. But then I want to divide that by all the ways that are the same. That is, I can rotate the people around the table, but keeping the same neighbors. And since there are 1, 2, 3, 4, 5 different places I could start seating person A and keeping the same arrangement, I would divide this by 5. So there are only going to be 4 times 3 times 2 times 1 different ways to seat 5 people around a table where only neighbors matter. So that works out to, I believe, 24. 4 times 3 is 12, times 2 is 24. Yeah, so there are 24 different ways to seat those 5 people around a table. Okay? So this is the last of these counting rules, these basic counting rules that we're going to go over. So in the next section, we're going to look at a little bit more advanced ways to count using permutations and combinations. And then we're going to apply that to some probability. All right, that's all for this video. I'll see you guys in class.